Are you able to see my PPT?
Yes, sir. Your PPT is visible.
And my audio is clear, na?
Yes, sir.
So this is the problem which we have discussed in last class. So this is two-cup arrangement used to measure the viscosity. This detailed discussion we had. Actually, this is the equation for viscosity. If say this is wire with a torsion constant Kt and theta gives the angular momentum of this suspended bob that can be measured by using mirror and laser. Then this is 4 is constant, pi is constant, omega 0 is a rotational speed of this outer cup, r is a radius of this outer cup, and L is the length of this suspended bob which is exposed to flowing fluid and free for moving, and kappa is the ratio of outer radius to inner radius. So we can measure the viscosity of given fluid using this equation. This is what we have discussed. So and this is what, okay, the Reynolds number, okay. So how this Reynolds number is defined for this case is omega square r, and this is variation, okay. So this is discussed. So just to summarize, so we have started our discussion on equation of change with a two-cup arrangement where this outer cup is rotating and inner cup is steady. Okay, this is kappa, this is r. Then second case we had, so outer cup is steady and inner cup is rotating. Okay, so this is same thing, two cup arrangement, but here inner cup is rotating and outer cup is steady. Then based on this case, so we had this viscometer, two cup viscometer. So where this inner cup is fixed with a suspended bob, free to move. This suspended bob is free to move. So I can estimate the torque. I can estimate the torque exerted by flowing fluid on this surface, and same torque will be exerted by this torsion wire. Hence, I can measure the viscosity of fluid in this cavity. This was the third case, and fourth case was this. This is very simple. We have just a one cup arrangement, and liquid is filled in this, and it is rotated. So it will take some concave surface at the top. Okay, concave surface at the top. So how to get this curvature of this shape? That is what problem we have discussed. So we have observed in all the cases, equation of change will reduce down to this simple form. This will give me theta. Okay, only there is a theta momentum. This will be a r component of theta momentum. This will be theta component of theta momentum, and this will be z component of theta momentum. Okay, so this will give me a velocity profile. This will give me a variation of pressure with respect to r, and this will give me a variation of pressure with respect to z. So so this all how to take the information. All four problems will, after substituting all the information, we are getting these three equations. This can be solved. If we solve this equation, I will get a velocity profile. If I solve this equation, I will get a variation of pressure with respect to r, centrifugal force, and this will give me variation of pressure with respect to g, okay, gravitational force. Variation of pressure with respect to z, this is because of gravitational force. Solving this, we can get different properties. Here in this case, we have say here we have derived the velocity profile. Here we have derived the velocity profile. Here we got the equation to estimate the viscosity based on this torsion constant and the moment of the substance theta theta moment of this suspended box. And in this we got this locus of the profile, top profile. Moreover, in this problem, there was one more additional information which we have learned actually. So this is the theta equation which is giving me theta velocity profile for this problem. And substituting in this, you can say R component. Substituting in the R component, this will give me variation of pressure with respect to R. substituting this in Z component, okay, we are getting some variation of pressure with respect to Z. Now solving these two equations simultaneously. This is all mathematical information. Okay, you might have solved so many problems like this in past also. Now simultaneously I need to solve these two equations. This is also variation of pressure with respect to R. This is also variation of pressure with respect to Z. So this is one method we have followed. So I have assumed for this, integrate this equation and assume this constant f1 such that which is a function of Z, okay, which has two components. One component is a function of Z and another is constant. Similarly, integrating this equation, this f2 is assumed this is function of R and constant. So overall pressure equation is this. So you can see if I differentiate with respect to Z, we will get this equation. If I differentiate with respect to R, I will get this equation. So this equation is a combined solution, simultaneous solution of pressure with respect to R and Z. This is multi-dimensional, single parameter multi-dimensional differential equation. Now if I have any one boundary condition, so I can get the value of C and get the locus of this point actually. So any confusion over this slide and this slide? Anybody has any confusion? Yeah, Pratish, are you able to hear me?
Yes, sir, I can.
You just keep me updating, okay? You are able to hear me. So
Yes,
whenever
sir,
I'm
yes.
asking, no doubt in this four cases and this solution of single parameter, single variable, multi-dimensional differential equation. Variable is pressure only, but dimensions are R and Z. Single variable multi-dimensional differential equation simultaneously solved to get this equation. And if I have one boundary condition, for example, here at Z equals to Z0 and at R equals to 0, pressure is atmospheric pressure. So I will get the locus of all the point which is having the top surface, locus of all the top surface of this point. Okay. Now today we'll solve this problem. A solid sphere of radius r. So this is solid sphere of radius r is rotating slowly at a constant angular velocity omega. So this is omega, and now this is sphere. So this will be a spherical coordinate system. So this will be my r direction. So a direction away from the center is my r direction, and this will be my theta direction, and this will be my phi direction. So this angular velocity omega is in phi direction. Okay, this is r, and this is theta, and this is phi. Okay, so this is spherical coordinate system. This is r, then theta. So theta is this. So r is this, moving from away from the center. So everywhere, this is r, this is r, this is r, and this will be theta. So if I move like this, round, 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 parallel to the surface, so this will be a theta. And if I move like this, okay, if I move like this will be my phi. So if I move like this, perpendicular to the surface, that will be a phi. So r, theta, and phi. A large, and it is immersed. Okay, body is immersed in constant fluid. Okay, large pool of the fluid actually, as shown in figure. So everywhere here is fluid. Everywhere here is fluid. Develop the expression for pressure and velocity distribution in the fluid. So I want to have, because this sphere is rotated in phi direction with the angular velocity omega. So I need to develop a velocity and pressure profile in the fluid. Fluid is here actually. This is solid sphere, so fluid is here. So I need to develop the velocity profile, how velocity is varying here in the fluid. So it fluid starts at r equals to capital R and ends at r equals to infinity, because this is constant fluid. Okay, infinite pool of the fluid. Okay, this sphere is dipped in infinite pool of the fluid. So torque and also develop the torque required to maintain this motion. So what will be the torque required? So some torque need to be applied. Some torque need to be applied so that because this fluid will be exerting resistance to flow. This fluid which is present here will be exerting resistance to flow. So that torque need to be provided. That resistance, opposite resistance to be provided, opposite force need to be provided so that there will be constant velocity of omega. It is assumed that sphere rotates sufficiently slowly. So there is no very fast movement of the sphere. So laminar flow and slowly at constant density and viscosity neglect the effect of gravitational force. So gravitational force effect is neglected. So whatever the variation of pressure is there, that is because of the centrifugal force and a variation of velocity, that the pressure variation will be there. Everybody got this point? Everybody got it?
Yes.
Number 53. Shivam. Roll number.
Yes, sir.
Yeah. Did you got the problem? Shivam.
Sir, he's writing in the chat box that he got it because he's having some mic issue.
Yeah. So now tell me. Roll number 59, Nikita. So which coordinate system you want to use, Nikita?
So we can use spherical coordinates.
Huh?
Spherical systems.
Spherical. So which will be non-zero velocity?
Non-zero velocity.
Huh?
1 second.
Which are the non-zero velocity? Roll number 64, Shubham.
Hello, sir.
So V phi, there will be velocity in the phi direction.
Non-zero. V theta is
Yes,
0, Vr is 0.
Yes, sir.
V phi is a function of r theta and z. R theta and phi.
V phi will be a function of theta, sir.
Theta and also r. If I am moving in r direction,
Yes.
So this is the problem. Spherical coordinate system. V theta equals to 0. Okay, V theta equals to 0, Vr equals to 0, and V phi is a function of r and theta. V phi is not function of phi because problem is symmetric around phi. Problem is symmetric around phi. Problem is not symmetric around theta. Hence, V phi is a function of theta. So V phi you can see. So here a velocity of the fluid here will be. So it is rotating with angular velocity omega. So this will be r sine theta. So r sine theta, so it will be highest at this point, again going 0. So here velocity, high velocity will be 0. If I am moving in theta direction, it is increasing. It will be maximum here. So this will be maximum high velocity at theta equals to 90. Again it will decrease. Again it will be a, you can say 0 at theta equals to 180, again 270 maximum, again 360 0. So V phi is a function of theta, V phi is a function of r. If I am moving in r direction, here velocity will be r omega sine theta. If I move in r direction, because this is large pool of fluid, so whole fluid will not be moving. At some r equals to infinity, velocity will be equals to 0. Hence, V phi is a function of r. So, and pressure is a function of r and theta. R because of centrifugal force, theta because of gravity and centrifugal force. This is not because of just a gravity. This is gravity as well as centrifugal force. Moreover, this gravity is neglected considering this diameter of this solid ball is smaller as compared to a thickness of the pool. Okay, pool is very large and diameter is very small. So pressure is function of R because of centrifugal force, and pressure is function of theta because of centrifugal force and gravity. Okay, this is what. And boundary condition. Now anyway we will be using a equation of change and phi equation of change. Okay, will give me a velocity profile. Theta equation of change, theta and R equation of change need not to be used, and this phi equation of change, phi component will give me a velocity profile, R component will give me a variation of pressure with respect to R, and theta component will give me a variation of pressure with respect to theta. This you should understand now, which equation of change will give you which information. Okay, and these are the boundary conditions. So you can see at R equals to R, means at all this surface, Vr equals to 0, V theta equals to 0, and V phi equals to R omega sine theta. So now you can see this is rotating with omega. So R omega will be the length of this thing actually here, and this sine theta, it is changing actually. This length of momentum is changing R sine theta. So you can get all this at R equals to R, V phi equals to R omega sine theta. At R equals to infinity, at very far from this solid sphere, at very far from this solid sphere, Vr equals to 0, V theta equals to 0, V phi equals to 0. And at R equals to infinity, pressure is given, pressure of the fluid. That is what the boundary conditions are there. So using this boundary condition, I can get the variation of pressure with respect to R and theta. And using this boundary condition, I will get the velocity profile of V phi velocity profile. So a Navier-Stokes equation can be used. Okay, this is Navier-Stokes equation for cylindrical coordinate system. Navier-Stokes equation of cylindrical coordinate system. This is R equation of motion. This is theta equation of motion, and this is phi equation of motion. So roll number 72, Mitali.
Yes, sir.
So what is your expectation? What you will get if we solve this R equation of motion? What you will get R equation of motion?
Sir, we'll get 0, sir.
No, this is variation of pressure with respect to R is there. No? Just now I explained everything. This
Yes, sir.
equation will give me a variation of pressure with respect to R. And what outcome you will get after solving theta equation of motion? Mitali?
Yes, sir. Sir, the same thing we'll get, sir.
Same thing. This will give me variation of pressure with respect to theta. This will give me
Yes, sir.
variation.
We'll get with respect to R pressure variation, and this will get with respect to theta the pressure variation.
And how about theta equation of motion? What you will get after solving this?
After solving this one, sir, this I guess phi with respect to velocity. So we'll get I guess velocity profile.
Yeah, you will get a velocity profile. So this is what you will get actually. So this is R equation of motion. So this is 0 because of steady state. Vr equals to 0. Hence this is equals to 0. This is also equals to 0. Vr equals to 0. This is equals to 0. Vr equals to 0. So this V theta is 0. V phi is non-zero here. V phi is non-zero. So this is 0. This is non-zero. And this is non-zero because pressure is varying in R direction because of centrifugal force. This VR equals to 0, hence this is equals to 0. This VR equals to 0, this is equals to 0. This is VR equals to 0, this is gravitational force is neglected. Okay, gravitational force is neglected, hence GR equals to 0. So this V phi square divided by R and del P by del R, these are non-zero. Okay, these are non-zero. So this is what I will get actually. This is what I will get. This is R component after substituting all the information, and this will give me a variation of pressure with respect to R. Similarly, a theta equation of motion, this is 0 because steady state V theta equals to 0, hence this is equals to 0. This is equals to 0 because V theta equals to 0. This is 0. This is non-zero. This is V theta. This is V theta equals to 0, hence this is equals to 0. This is V theta equals to 0, and this will be non-zero. V phi square cot theta divided by R square. This will be non-zero, and this will be non-zero. This is 0. V theta equals to 0. This is 0. V theta equals to 0. This is 0. V theta equals to 0, and this is 0. VR equals to 0. This is 0 because V phi is not a function of phi, and G theta equals to 0, and this will give me a variation of pressure with respect to theta. That is what I was telling, that pressure is varying in theta because of gravity and centrifugal force, and this will give me information related to centrifugal force only. Okay, centrifugal variation of pressure with respect to centrifugal force. So because we are neglecting a gravitational force, because this diameter of the ball is smaller enough to consider the variation of gravitational from this point to this point, hence gravitational force is neglected. This will give me theta component. Okay, so this is what R component will give me variation of pressure with respect to R, and theta component will give me a variation of pressure with respect to theta. Now this is phi component. This is 0 because of steady state. This is 0 because of VR equals to 0. This is 0 because of V theta equals to 0. This is 0 because V phi is not a function of phi. V phi is not function of phi. V phi is a function of R and theta only. And this is 0, VR equals to 0. This is 0, V theta equals to 0. This is 0 because pressure is not function of phi. Because problem is symmetric around phi. Problem is symmetric around phi, and this is 0. And this will be non-zero. This will be non-zero. V theta is a function of R, so this is non-zero. This is V phi. This will be non-zero. This is non-zero. Then V phi is not function of phi. This is 0. VR is 0. V theta is 0, and G phi equals to 0. So what you will get? You will get this equation. So this is non-zero. This is first non-zero term, and this is second non-zero term. And this, after solving this, what you will get? A velocity profile. To solve this, I need at least two boundary condition V phi with respect to R and theta. Two boundary conditions. Is 2 with respect to R and 2 with respect to theta. Now overall problem boils down to, so this is what theta component. Phi component will give me a velocity profile. Theta component will give me a variation of pressure with respect to theta, and R component will give me a variation of pressure with respect to R. These are all available boundary conditions. So anybody has any doubt over this slide? Roll number 77, Tejas.
Got it, sir.
Got it. Very good. Roll number 88, Pratish.
Yes, sir.
Got it. Anybody has any doubt over this slide? This is everything about problem. So we got all the information from the problem, and these are the simplified equation of change. These are the simplified equation of change. Theta component will give me a velocity profile. No, phi component will give me a velocity profile. Theta component will give me a variation of pressure with respect to theta, and R component will give me a variation of pressure with respect to R. Now, to get the torque, we need a velocity. Okay, we need to calculate the drag force exerted by fluid on this surface multiplied by moment arm. Okay, how to get the torque? I need to estimate the torque. So how to get the torque? Torque will be a drag force exerted by fluid multiplied by moment arm, and over this sphere, whole surface, that will be a torque. That is what I want. So for that, I need a velocity profile. So how to solve this equation? Anybody has any idea? Can anybody give me any idea how to solve this equation? This is single variable multi-dimensional differential equation, not simultaneous. This is not simultaneous. Roll number 6, Aksh.
Yes, sir.
Any idea how to solve this equation? And you need to keep in mind that there can be more than one way to solve the problem in mathematics. Okay, there is no single way, or most of the time there can be more than one way, but answer will remain same. Answer will remain same. Anybody else? So here one technique is there. You will assume some solution first of all. You will assume some solution first of all, so that one variation, one dimensions will be eliminated. Your assumption of solution should be such a that after substitution, one dimensional variation will be eliminated, and then we will left with a variation with a one dimensions only. Like here, V phi is varying with R, V phi with varying with theta. So I will assume some solution for V phi such a that one of the variation will be eliminated. Such a assumption, this is solution. I don't know what is f of r. Some function of r into sine theta. So this is assumed solution. V phi equals to function of r into sine theta. So if I substitute this now, you substitute this. F is a function of r only. F is a function of r only. It is not a function of theta into sine theta. So I am assuming velocity profile in this format. V phi will be equals to function into sine theta, where function is a function of r only. It is not a function of r and theta. Now substitute here and see what you will get. Substitute this V phi here. V phi equals to f of r into sine theta. And substitute V phi equals to f of r into sine theta here. Substitute and simplify. Roll number 16. Roll number
Yes,
16.
sir.
Yeah. Datta.
Yes, sir.
Roll number 16.
16, 1, 6.
So why you are logging with mobile as well as computer also?
Sir, I don't know. Sir, I was having a trouble with my Wi-Fi, so I logged in from mobile. I don't know how I got logged in from PC.
You don't.
I'm not.
Oh, you don't know.
I'm not.
Okay, okay.
No, I'm just on
Okay.
mobile. I'm talking with you
So
from mobile.
what you will get after substituting here? So this is function of r into sine theta. So you can take out this sine theta out. So this term will be a sine theta divided by r square d by dr of r square d by dr of f. Okay, d by dr of f. Okay, Datta? This is okay?
Yes, sir. Yes, sir.
How about here? If I substitute here, so what you will get? F of r into sine square theta. So f of r you can take out directly outside, because f of r is not a function of theta. So this f of r will be taken out, and here I will left with a sine square theta. D by d theta of sine square theta with 2 sine theta into cos theta, and this sine theta will get cancelled. So remaining is 2 cos theta, and 2 cos theta. What is the integration of 2 cos theta will be a minus 2 sine theta. Minus sine theta. not 2, yeah, 2 will be here actually, and minus 2 sine theta. So, and this r square, and this you can sine square theta divided sine theta divided by r square. Here also you will get sine theta divided by r square, and so after rearranging, so you should be getting this equation. Yeah, sine theta divided by r square, sine theta divided by r square is common, and this is as this is 0. So 0 divided by this will be a 0, and you will be getting only this term and only this term. Yeah, roll number 20, Aviral.
Yes, sir.
Did you got this equation?
Yes, sir.
Yes. Can you show me your notes?
Sir, can you wait for a second? I'm sure.
Why need to wait? Because you got the equation, na? Aviral. Anybody got this equation?
Yes, sir.
Aditya. Aditya, you got it?
Yes, sir.
And this is a standard differential equation. This is standard differential equation. And what will be the solution of this differential equation? So if you go in mathematics, differential equation, so d2 by dr square minus f of r by dr square f of r minus f of r, that equals to 0. This is standard differential equation, and this can have a standard solution. Standard differential equation or standard solutions are given. Anybody else is getting this equation? Roll number 60 got it. Anybody else can write in chat box?
Yes, sir, getting.
Okay, very good. So this is the standard differential equation, and this equation have a solution of this form. Sometime it will be written in exponential form also. Sometime it will be written in sine cos form also. Sometime it will be written in hyperbolic sine, hyperbolic cos also. It all depends upon format of this standard differential equation. So this is the standard differential equation which will have solution of this format. F equals to C1 R plus C2 divided by R. And I know V phi is a function of R multiplied by sine theta. So what will be velocity profile? Velocity profile will be a V phi will be equals to C1 R plus C2 divided by R square sine theta. Okay. So now this is, everybody got this? Here roll number 42, Rishikesh. Roll number 42. Roll number 49, Harshavardhan.
Yes, sir.
You got this velocity profile with constant C1 and C2.
Constants I'm solving, sir.
Yeah, for this you need to revise all your mathematics actually. This is one problem where we are getting this format of differential equation. It can be of any format, and accordingly you will get a solution. And this you need to cover all differential equations. Okay, this is one standard differential equation. We'll have solution of this format, and after substituting this will be my velocity profile. Harshavardhan, you got it?
Yes, sir.
So what will be the value of C1 and C2, Harshavardhan?
C1 will be 0.
C1 will be 0. Why?
We apply the boundary condition. R equal to R, velocity is 0.
So at R equals to R, velocity is 0. at r equals to r, velocity is 0. How c1 will be 0 using that? Here roll number 50, Rashmi.
Yes, sir.
C1 equals to 0. How?
Sir, 1 second. Sir, sir, I'm still solving. So, like,
There is nothing
when
to solve. There is nothing to solve. You are still solving, but there is nothing to
so
solve.
like logical, some like
Very good, very good. Logical means what?
logical. So logical boundary condition. So like we know that we should be finite, but then if we are putting r is equal to infinity,
Excellent.
like
Excellent.
r equal
So
to 0,
using
it
this
will
boundary
be
condition, using this boundary condition at r equals to infinity, v phi equals to 0 or v phi is finite. If I put r equals to infinity and c1 has some value, then what is v phi? V phi will be equals to infinity. If r equals to infinity, c1 has some value, then certainly this will give me infinity value for v phi. Hence, this term should not be there, or I can call it as a c1 equals to 0. Now c1 equals to 0. Now using this boundary condition at r equals to r, c1 equals to 0 at r equals to r. So at r equals to r, v phi equals to r omega sine theta. So what will be c2 equals to? Rashmi?
so C2 will be r square. No, so 1 second. Sir, V2, sorry, C2 will be r square omega sine theta.
So this no sine theta will get cancelled, na?
Oh, yes, sir, r square omega, sir.
R cube. Here you will get r square, and here also one r is there.
Yes, sir. Sir, I was just solving. Yes, sir, omega r.
C1 equals to 0 and C2 equals to omega r cube. So what is velocity profile? This will be my velocity profile. So you can see this velocity profile is a function of r and theta. So this will give me variation with respect to r and theta. So given a value of r and theta, so I will get a velocity v phi. How v phi is varying. Okay. Now I need to estimate the torque. Okay, this is velocity profile. So everybody got this velocity profile. Now torque. How to get the torque? Torque exerted by flowing fluid on a spherical surface. First of all, I need to calculate a drag force. Okay, for drag force, I need to calculate a shear stress. Shear stress exerted by flowing fluid on a surface multiplied by surface area will give me a drag force multiplied by moment arm will give me a torque. Okay, so this will be a shear stress exerted by flowing fluid, and this is shear stress momentum flux because of phi velocity at r equals to r multiplied by surface area. This will be a surface area actually. R square sine theta d theta d phi, and it varies from theta varies from 0 to 2 pi and phi varies from 0 to pi. Okay, this will vary from 0 to 2 pi and this will vary from 0 to pi. Okay. So this will give me a drag force exerted by flowing fluid. A drag force exerted by flowing fluid on a surface multiplied by moment arm. Lever arm will be r sine theta. And if I integrate between theta 0 to 2 pi and phi 0 to pi, that will give me a torque. Okay, if this is integrated, this is phi theta varies from 0 to 2 pi and phi varies from 0 to pi, tau r theta estimated at r equals to r sine theta. So this will be r square sine theta. So r square sine theta d theta d phi. Okay, this will be a torque. Okay, this is what I want. Now substitute how to get tau rz. So you can use the Newton's law of generalized Newton's law of viscosity. So this is using generalized Newton's law of viscosity. Tau rz will be equals to minus mu 1 upon r sine theta d by d phi of Vr plus r d by dr of v phi into r. Now substituting this is Vr equals to 0. Anyway, this term will not be there. Substitute v phi here and differentiate with respect to r. You will get tau r theta and estimate at r equals to r. Estimate at r equals to r and integrate between 0 to 2 pi theta and 0 to pi theta, and this will give me a torque, value of torque. Okay. Anybody has any confusion over here? Here, roll number 72. Himani.
Understood, sir.
Mitali, yeah. What the problem? How to solve this?
Yes, sir.
Okay. So you go home and do all the mathematics. Okay. Everybody go home and do all the mathematics. Hope you understand the process. How we got? How we got is, so using velocity profile, we'll be getting this surface momentum flux, and this momentum flux at r equals to r. Okay, this will be momentum flux at r equals to r multiplied by surface area. Okay, this will be a surface area. This will be surface area. That will give me a drag force. Drag force multiplied by this moment arm. This is the arm moment, r sine theta. And this, it is changing because I am moving in phi direction. And this whole will be a torque for a surface area d theta d phi, and it is integrated over 0 to pi for d phi and 0 to 2 pi for theta. That will give me a total torque exerted by. And how to get this tau rz? This is generalized Newton's law of viscosity for spherical coordinate system, tau r phi, and this is Vr equals to 0. Substitute v phi, this is v phi in this equation, and differentiate with respect to r divided by r, and at r equals to r. So at r equals to r, so you will be getting this equation. Now integrate this equation with respect to theta and phi. This will be sine cube theta d theta. So, and theta varies from 0 to pi. So integrating this equation, you will get 8 pi mu omega r cube. Now, just quickly, we'll take a look over a dimensional analysis of equation of change. So you have used so many methods for dimensional analysis for different equations. So most important, yeah, tell me.
Sir, in the start, we assumed v phi equals to a function of r and into sine theta. How did we got that?
This you mean to say, no?
Yeah, yes, sir.
Look,
We have to eliminate.
What will be velocity here at this point?
0.
0. So here velocity will be maximum.
Yes, sir.
Okay. So, and some function of r is there. I don't know what is the function of r, but if I am moving in theta direction, it is a function of sine theta. Can you see? Sine 0 equals to 0. Here
Yes,
sine
sir, yes.
90 equals to maximum. Again sine 180 equals to 0. Again sine 270 is maximum 1, and again sine 360 is 0. So certainly some function of r into sine theta. Just logic. So you need to observe the problem. It depends upon each and every problem. Here I know that my velocity is a function of r, but how it is changing in theta direction? Here it will be minimum, here it will be maximum, again going down, again going up, again going down. Okay, and that exactly how sine theta is behaving.
Yes, sir.
Hence, hence this assumption may be the solution. This may be the possible solution. Okay, this may be the possible solution. Hence, I have assumed V phi is a function of R into sine theta. Okay.
Okay, sir. Got it.
Who is talking? Roll number
103.
Saurabh.
Yes, sir.
Okay. So now we will quickly go through a dimensional analysis of equation of change. So what is the importance of dimensional analysis is so that we can involve some of the dimensionless number in a given equation. Or given equation can be explained with some dimensionless number such that it can be applied. Experimental observation can be applied to an industrial level observation, actually can be correlated. Okay, that is what importance of dimensional analysis. So we'll apply this dimensional analysis. So this is equation of continuity, equation of continuity for incompressible fluid. Density is constant, and this is equation of change. This is equation of change. Now I am using a characteristic length L0 for dimensionalizing the length. This L0, for example, for flow through pipe, a diameter of the pipe is a characteristic length. Characteristic velocity V0 is used to dimensionalize all velocity present here, which is average flow velocity, flow through pipe. Again, example, you can take flow through pipes. So you can have bulk velocity for lower flat plate, characteristic velocity, and this is characterized modified pressure. This can be taken. This is exit pressure. Tube exit pressure is used as a characterized pressure. So, so this x bar substituting x bar equals to x by L0, dimensional length. This is called as a dimensional length. Y bar equals to y divided by L0. This is dimensional width, and this is dimensional thickness, x, y, z direction. Then this is t. This is dimensionless time. Dimensionless time using average velocity and length. So, and this is velocity, dimensionless velocity. This is dimensionless pressure. This is again dimensionless pressure. This is one way of dimensionalizing the pressure. This is another way of dimensionalizing the pressure. This is the definition of del. Okay, so del dimensionless will be a L0 into del. So that this is the definition of del. This is the definition of del square dimensionless, and this is the definition of substantial time derivative dimensionless. Okay, substituting all this in the definition of del square and substantial time derivative, I will get this is the definition of del dimensionless, del square dimensionless, and substantial time derivative dimensionless. Now substituting everything, all this information. So this equation of change is changed to this format. d by dt dimensionless. This is dimensionless equation. This is dimensionless pressure of one format. Mu L0 V0 rho divided by del square V. And this is another pressure format, dimensionless. There are two pressure dimensionless. So using this, I will get this equation, and using this pressure definition, I will get this equation. Okay. Now this you can say L V rho divided by mu, d V rho divided by mu. This is Reynolds number. So this is the equation of change in dimensionless form will be equals to dimensionless pressure multiplied by Reynolds number del square dimensionless velocity. Here this is a Reynolds number. This is 1 upon Reynolds number, actually 1 upon Reynolds number. Now if R equals to infinity, what you will get? You will get this equals to 0. So this equals to 0. Viscous forces are neglected. Viscous forces are neglected, and this equation will change down to this for R equals to infinity. Similarly, using a second dimensionless equation. So this is called as the Euler equation of change. Sometime based on situation, sometime we can start with this Euler equation, simplified form of equation of change, and solve the problem. And if say second equation of change, this is again a 1 upon Re. This is again 1 upon Re. So if Re is very small, okay, Re is very small. So what we will get? This is equals to 0. This is equals to 0. Okay, this is equals to 0. This is equals to 0. So what you will get? You will get a non-accelerating flow, and this kind of flow is called as a creeping flow. Just now we have seen an example where it was rotating very small, very low velocity. So certainly Reynolds number will be very small. Reynolds number is very small. So this will be equals to 0. This will be equals to 0. So that will give me a creeping flow or non-accelerating flow. This is called as a non-accelerating flow. This is what dimensional analysis of equation of change. So for more practice, you need to concentrate on all the problems given in chapter number 2 and chapter number 3 of BSL transport phenomena, so that you can be more familiarized with using a equation of change. This is all we are going to cover equation of change. In next class, we will be starting a shell balance approach for heat transfer. So anybody has any difficulty can discuss. Roll number 97, Sridhar.
Yes, sir.
Yeah. Any difficulty in this equation of change and shell balance? Now hereafter, we will not have much discussion over momentum transfer. Now momentum transfer is over. All the portion which we are supposed to cover related to momentum transfer is over. Now what we will be going to discuss in coming classes will be a shell balance approach for heat transfer, shell balance approach for mass transfer, then a little equation of change for mass transfer and heat transfer. That is what we are going to cover. Heat transfer and mass transfer, shell balance and equation of change. Momentum transfer is over. Everything is clear, Sridhar?
Yes, sir.
Okay. Anybody else has any doubt?
Hello, sir. Am I audible?
Yeah, 63. Yes.
Sir, how we got that if RE is very less than 1, then both the terms are 0. How we got that?
This will be also infinity. This will be also infinity actually. Infinity. This is minus
Oh, okay,
infinity.
okay.
This
Yeah,
plus
yeah.
infinity.
Okay, got it, sir.
Okay, then thank you very much. We'll start our
Hello, sir.
tomorrow's class. Yeah, Pratish.
Sir, could you please share the recent recording?
Yeah, we'll share. We'll share all the recording.
Okay.